Okay, we've got a pretty interesting integral here. We've got something, got an integral from 0 to 1, x to the fourth, 1 minus x to the 10th, all cubed dx. Okay, and of course you could just multiply this out, right? We could just cube this out, and then use the power rule, but I don't want to do it that way. What I want to notice is the similarity that we have here to the beta function. Okay, so we'll look at our beta function real quick that we have here on the board. And what this allows us to do is we actually get our integral and we can go right to our solution in terms of the gamma function as we have it over here. And this is pretty nice because the gamma function, it looks like I lost a parenthesis, but the gamma function, we can usually calculate that pretty easy using the factorial. But the one problem we have is in our original integral here, we have that exponent here. We have that 10 on this x. So that's the thing we need to deal with. If we can get it into this form, then we can use our beta function and then jump to our solution. So let's go back and look at our problem. Okay, so what I can do from here is we can use a u substitution. We want to just handle our real problem is this x to the 10th. But if I do a u substitution and I make my u equal x to the 10, then by doing that, hopefully this works out into the form that we want. So let's see what happens when we take our derivative here. So we're going to have 10x to the 9th dx. I'm just going to solve for dx. So our dx is going to be du over 10x to the 9th. Okay, we'll make our substitution, but what I'm going to do first, we just have this 1 over 10 here. I'm going to bring that out front as a constant. Bring that in front of the integral. Plug in a 1 into x to the 10th, we get 1. Plugging in 0, we get 0. Then, let's see, I'm just going to leave, even though we're substituting into u, we want everything in u, but I'm going to leave our x for the moment. And we'll deal with that in a second. Then we're going to have our x to the 9th here. This transforms nicely into 1 minus u cubed du. Then we'll do this division here real quick. Canceling x to the 4th divided by x to the 9th is just x to the 5th. So let's do a quick rewrite, a quick cleanup. Now, actually, one thing you'll notice, oh, and sorry, this is actually an x to the minus 5th because of the 9 in the denominator. Now, we'll notice if you have the square root of u, that's going to be, using this, that's going to be x to the 5th. Well, if we have 1 over square root of u, or u to the minus 1/2, then we have x to the minus 5. And that's what we have here. So when I do that rewrite, let's use our u to the minus 1/2. So we're going to have, let's use a different color though. So we're going to have 1 over 10, integral 0 to 1. We'll have u to the minus 1/2, 1 minus u cubed du. Okay, and here's where we bring our beta function into play because now we're in exactly the right format, right? We just have an exponent on our u, and we have, this is now 1, so we just have this 3 to deal with. Now, oh, and I do have a typo here. This is c2 minus 1. So when we get our solution, we need to add 1 to everything. So let's see how this is going to look. We'll just bring our solution down here. So we're going to have 1 over 10. Okay, and then our solution, our z1 is going to be minus 1/2 plus 1. Okay, because this is z minus 1 here. So we're going to have gamma of 1/2, okay, times gamma. Then we need to add 1 to this one. So we're going to have gamma of 4. And then here we're going to have gamma of the sum of these two, which is going to be 4 plus 1/2. Okay, so from here, the challenge is just trying to get ourselves like a decent numerical answer. But we kind of have an answer here, but let's try to clean it up a little bit. We'll have our 1 over 10 in front. Now, gamma 1/2 is like a very common value. We could solve that through like the gamma function and doing an integral. That's a bunch of work though. This is actually, what I find is it's just nice to know this value and just kind of keep it around rather than try to like prove it every time. And this is just the square root of pi. Gamma 4 is easy. So with integer values, we can just go to a factorial. So gamma 4 is actually the same thing as 3 factorial or 6. We'll leave it as 3 factorial for now. And then here, this thing's a little tricky to deal with. Now there's a few different ways to deal with this. Now let's see, gamma of 4 plus 1/2. I think what I'm going to do for gamma of 4 plus 1/2 is let's deal with this separately because it's actually not too bad. The numbers aren't that big. So let's just bring this over here and deal with it. Okay, for this value of gamma of 4 plus 1/2, we could just write this. I have this kind of set up like if you're going to use a formula, it's nice to have it in this format. But really for what we're going to do, I'm just going to add those together and get 9/2. Again, with the gamma function, to get to a factorial, we just subtract 1. Okay, so we're looking at 7. I didn't really need parentheses, so we got 7/2 factorial. Now what we can do with this real quick, okay, because it's a factorial, we can just kind of write it out and write it as 7/2 times 5/2 times 3/2 times 1/2 times minus 1/2 factorial. Okay, but the thing with that is minus 1/2 factorial is the same as gamma of 1/2, and we just talked about that value, and that's just this known value, square root of pi. So again, it's kind of good to reuse this or kind of just work backwards. Knowing this one value can get you a lot of other values. So all we need to do is multiply this together, knowing that this thing is square root of pi right here. Okay, we can just multiply this out, and we're going to have 7 times 5 times 3, which is 105. 2 times 2 times 2 times 2. 2 to the 4th is 16. We bring down our square root of pi, and we have this value. Let's go back to our what we were evaluating and just kind of plug this thing in. Okay, so here we are. We're going to plug in 115 over 16 square root of pi. But because the 16 is in the denominator here, I can bring this up to the numerator, okay, just using like fraction properties. And then the nice thing here is we already have a square root of pi here. So we can cancel, and maybe just do like a little more simplification. So like we'll cancel a 2 here out, and we have 8, and this is 5. Sorry, I forgot to like cancel out a 3 somewhere. So 48 is 3 times 16. 525 is 3 times 175. Our 3's are going to cancel, and we're left with our final solution, 16 over 175. That's it. Pretty good problem. We'll stop it there. Thanks everyone for watching. Hope you all have a great day. Appreciate it. Take care. Thanks. Goodbye.